In the last lesson, part 1 of our introduction to row spaces, we saw an example where we are supposed to determine if a certain row vector lies within the row space of a certain given matrix A. Now, I introduced two methods. The first method is where we make use of this theorem here that says that the linear system Ax equal to B is consistent if and only if B transpose lies in the row space of A transpose. So in this case, I have to form the linear system A transpose times X equal to W transpose and the augmented matrix made of A transpose and W transpose. And to prove that W does not lie in the row space of A, we have to show that the system is inconsistent. On the other hand, to prove that W lies in the row space of A, we have to prove that the system is consistent. I also introduced a second method to solve the same problem, where I append the row vector W to the bottom of the matrix A. In this case, if the REF shows that the bottom row is not a zero row, then W is not linearly dependent on the rows of A. Therefore, we can conclude that W does not lie within the row space of A. Conversely, if the appended row, as in part B, is reduced to a row of zeros, then can conclude that W is linearly dependent on the rows of A, and therefore W lies in the row space of A. I also mentioned an important point whereby you can't swap the appended row with any other rows of the matrix A in order for the method to work. And I specifically come up with an example that shows that if you were to swap rows, then you will end up with a wrong conclusion. In this lesson, I will talk about finding a basis for the row space of a certain matrix A. But first, let me introduce an important theorem that links the row space of a matrix and the elementary row operations. Suppose A is an m by n matrix that has been row reduced to its row echelon form R, then row space of A is equal to the row space of R. That is, the elementary row operations do not change the row space of a matrix. Now, the proof of this is quite simple. We first let our matrix A be the matrix of the row vectors R1, R2, all the way to Rn. And this is an m by n matrix. Now let's prove this statement here for all the three types of elementary row operations. First, let us define the row space of A, and it is the span of the rows of the matrix A, which is given as the set of all vectors such that we have C1R1 plus C2R2 plus all the way to Cm such that C1, C2, all the way to Cm are real numbers. First, we show that swapping rows will not change the above span. So, for example, if we were to swap row 1 and row 2 in the matrix above, this implies that our row space of A now becomes the set of all vectors such that we have C1, R1, C1, R2 plus C2R1 plus all the way to Cm, Rm such that C1, C2, Cm are all real numbers. Now you can see clearly that if you were to rearrange these two terms, this is actually equal to C2R1 plus C1R2. Now, whether the coefficient of row 1 is C1 or C2, they are still the set of all real numbers, which means that the span that you see here is the same span as the original row space of A. So therefore, swapping rows will not change the original span. Now let's talk about the second kind of elementary row operations. That is, if we were to multiply a certain row by a certain non-zero scalar, k, and that will not change the span either. So for example, multiply row 1 by the scalar k. So in this case, the row space of A becomes C1 k row 1 plus C2 row 2 plus all the way to CMRM, such that C1, C2, Cm are all real numbers. But from here we know that C1k is still a real number, which means that this row space here is the same space as the original row space of A. And therefore, multiplying a row by a non-zero scalar will not change the span either. Finally, we consider the third type of elementary row operations, adding a multiple of one row to another row. For example, if we were to add the scalar d times row 1 to row 2, so now our row space of A becomes C1R1 plus C2, here is actually replaced by row 2 plus d times row 1 plus all the way to CMRM, such that once again C1, C2, all the way to Cm are real numbers. And we can rearrange this span to obtain this expression here, C1 plus C2d row 1 plus C2 row 2 all the way to CMRM, such that now this is just the above expression. For convenience, I will not write them down. Now, this expression here, C1 plus C2d, is still a real number, which means that this is still the same span as the original row space of A. So in conclusion, we say that the elementary row operations do not change the row space of a matrix. Here we invoke a theorem to find a basis for the row space of the matrix A. Suppose matrix A has been reduced to its row echelon form R. Then we can say that the non-zero rows of R form a basis for the row space of R. Now the row space of R is the span of the rows of R. But the non-zero rows of R are obviously linearly independent, since R is in row echelon form. And the staircase pattern means that the pivots are in different columns. For example, let's consider this matrix here in row echelon form. We have 1, 1 minus 3, 0, 2, 1, 0, 0, 0. This is the row echelon form that you see in one of the previous examples. Now the pivot is here and here. Okay, so we have a staircase kind of pattern here. Now there are two non-zero rows, the first and the second rows, with pivots in different columns. And we can see clearly that none of these two rows are scalar multiples of the other row. Therefore, these two rows are linearly independent. And furthermore, since row space of A is equal to the row space of R, the non-zero rows of R form a basis for the row space of A. Now, armed with this theorem, we are now finally ready to go through a few examples on finding a basis for the row space of a matrix. Now let's take a look at an example of finding a basis for the row space of a given matrix. Part A, find a basis for row space of A where A is a 2 by 3 matrix. So we first reduce this to the row echelon form, REF. We know that this is the pivot, therefore we have to get rid of this term below the pivot. So our first operation, row 2 becomes row 2 minus row 1, and that will give us 1, 0, minus 1, and 0, 1, 2. And let's call this the matrix R. This R is already in a row echelon form. Therefore, from the previous theorem, we note that the non-zero rows of R form a basis for row space of R, which means that these first two rows here, which are non-zero, form a basis for the row space of R. Now, from point number 2, we also know that because the row space of A is equal to the row space of R, therefore, the same non-zero rows of R also form a basis for the row space of A. Therefore, we conclude that a basis for the row space of A is given by 1, 0, minus 1, and 0, 1, 2. Now take note that these are row vectors because we are talking about the row space of a certain matrix, and this is our answer for part A. For part B, the same method applies. Our matrix A is given by this 3 by 3 matrix. And we can perform the row operations to reduce this to REF form. The first operation is to get rid of this number here below the first pivot. We obtain this matrix. And the second operation is to get rid of this number below the second pivot. And we obtain this matrix. And this is our REF. And let's call this R. So once again, we can conclude that a basis for row space of A is equal to the non-zero rows, which are the first two rows. 1, 1, minus 3, and 0, minus 2, minus 1. So that's our answer for part B. Now let's take a look at another type of problem where we are supposed to find a basis for the row space of the matrix A formed from the rows of A. Now notice in our previous example, our basis for the row space of A is formed from the rows of the row echelon form R and not from the rows of the original matrix A. So in this question, we are supposed to find a basis for row space of A formed entirely from the rows of A, which means that your basis vectors are to be selected only from the rows of the matrix A. You cannot use the row vectors from the reduced echelon form R. For part A, this matrix was already introduced earlier. From the previous solution, we know that the REF is 1, 1 minus 3, 0 minus 2 minus 1, 0, 0, 0. And this is equal to our R, the row echelon form. Now, if there were no restriction on where the basis vectors come from, then we can just easily take the first two rows of the matrix R. But now we are supposed to form our basis entirely from the rows of A. So what should we do? Now, previously we know that a basis for row space of A is equal to the first two rows of your matrix R. Now, since there was no swapping of rows involved when we reduced matrix A to the matrix R, therefore an alternative basis for row space of A will just be in the rows of A corresponding to the non-zero rows of R, which means that we can simply take the first two rows of A as our basis vectors. So therefore, the basis will be 1, 1, minus 3, which is the first row of A, and 1, minus 1, minus 4, which is the second row of matrix A. So therefore, we have found a basis where the vectors are taken entirely from the rows of A. Now, once again, this method works because there was no swapping of rows involved when we reduced matrix A to matrix R. What if there has been swapping of rows involved? In that case, you have to take care of the positions of the rows after they are being swapped. It is still possible to apply these methods, but you have to keep track of the positions of the rows being swapped, as I will illustrate in the next solution. For part B, we are given a 3 by 5 matrix. And now we purposely swap row 1 and row 3. Okay, let's see what happens. Swap with row 3, and that will give us and finally, after some row operations, we arrive at the row echelon form. Let's call this row echelon form our matrix R. Now, these operations here do not involve any swapping of rows, so we just say as a note, no swapping of rows in this set of operations that bring this matrix to the REF matrix R. Now we know that a basis for row space of R will just be the non-zero rows from the matrix R, which are the first two rows and this will also be a basis for the row space of A, according to our previous theorem. Now, what about a basis that consists entirely of rows from the matrix A? Now, here is where it gets interesting because we have to keep track of the rows as mentioned previously. Recall that from this matrix to this matrix, row 1 will swap with row 3. So we can write down the row numbers here. This is actually 3, this is 2, and this is 1. Now the first two rows of R are the basis vectors for the row space of R. Therefore, the corresponding rows from the original matrix A will be row 3 and row 2. Now, once again, take note that these are the original row numbers. So what we should do is, we look at the original row numbers that correspond to the non-zero rows in the row echelon form. Therefore, we have to pick row 2 and row 3 from the original matrix. Therefore, we say that a basis for row space of A taken entirely from the rows of A will be row 2 and row 3, which are minus 1, 2, 1, 2, 3, and row 3, 1, minus 2, 1, 4, 4. And that will be our answer for part B. In this question, we are supposed to show that the two bases computed using the two different methods outlined in the previous two examples actually span the same row space. Now, if you recall this matrix A, we used two different methods to compute the row space of this matrix. For method 1, we are taking the non-zero rows of the reduced echelon form R, and then we said that a basis for the row space of A is equal to these two row vectors. And then for method 2, recall that we were using the rows from A corresponding to the non-zero rows from R. So we write rows from matrix A corresponding to the non-zero rows from the row echelon form R, and we said that a basis for row space of A would be 1, 1, minus 3, and 1, minus 1, minus 4. Of course, the difference of these two methods is that for method 1, the set of basis vectors are taken from the rows of R, whereas for method 2, the two basis vectors are taken from the rows of A. And in this question, we are supposed to show that they span the same row space. Now, the gist of our solution procedure is to show that the matrix formed from the basis vectors will reduce to the same RREF. So to elaborate for method 1, then on the right we have method 2. Let's form a matrix from the basis vectors as its rows. So for method 1 we have 1, 1, minus 3, 0, minus 2, minus 1. Now the rows of this matrix are just the basis vectors from method 1. Whereas for method 2, we call it A prime. Right? We also form a similar matrix from the basis vectors from method 2. In this case, we have 1, 1, minus 3, 1, minus 1, minus 4. Now recall that for a certain matrix that has been reduced from A to R, where R is the row echelon form, the row space of A is equal to the row space of R. Okay? And also for this matrix A prime, if this can be reduced to a certain row echelon form R prime, then we can also claim that row space of A prime is equal to row space of R prime. Now, if we can show that the R and the R prime here are the same, then this would mean that the row space of A is equal to the row space of A prime. And we would have shown that the bases, the two bases for the row space of A are equivalent. Now for matrix A, let's proceed to reduce it to RREF form. The first operation, we scale row 2 becomes half of row 2, and that will give us 1, 1 minus 3, 0, 1, half. And then the next step is to get rid of this term above the second pivot. So for that, we will have R1 becomes row 1 minus row 2. And that will give us 1, 0 minus 7 over 2, 0, 1 half. And this is actually the RREF of matrix A. On the other hand, for matrix 2, our first operation is to get rid of this number here below the first pivot. So R2 becomes R2 minus R1. So we have 1, 1 minus 3, 0 minus 2 minus 1. Now at this step, notice that this matrix here is exactly the same as this matrix here, which means that after a few more row reduction operations, we are going to arrive at the same RREF. So here, after a few more steps, we are going to arrive at the same matrix here, which is 1, 0 minus 7 over 2, 0, 1 half. And this would be the RREF of matrix A prime. Now, since the RREF of matrix A is equal to RREF of matrix A prime, therefore the row space of this RREF of A is also equal to the row space of this RREF of matrix A prime, which means that from a previous theorem, the row space of A is equal to the row space of A prime. Therefore, we conclude that the basis from the two different methods span the same row space. Our final example for this lesson involves finding a basis for the column space of the matrix A and the row space of the matrix A using the transpose. Now find a basis for column space of A and row space of A using A transpose. For part A, it is a 2 by 3 matrix. The A transpose will be equal to 1, 1, 0, 1, minus 1, 1. And this can be further reduced to row 3 becomes row 3 plus row 1. That's to get rid of this term here. 1, 1, 0, 1, 0, 2. And then further operation on this. Row 3 becomes row 3 minus 2 times of row 2. And that would give us the row echelon form 1, 1, 0, 1, 0, 0. Let's call this R. Now we recall that previously we say that row space of A is equal to column space of A transpose. Now, if we can find the column space of A transpose, we would have found the row space of A as well. But now, the basis for column space of A transpose is just equal to the columns of A transpose corresponding to the pivot columns of R. Now the pivot columns of R are obviously the first two columns because they contain the pivots. Therefore, the two columns of A transpose form the basis. And we have 1, 0 minus 1, and 1, 1, 1. Therefore, from this relationship, we deduce that the basis for row space of A, which is equal to the column space of A transpose, would be equal to, now converting these column vectors into row vectors, 1, 0, minus 1, 1, 1, 1. Right, so that is the answer for the row space of A for part A. Now, what about the column space of A? Now, recall that the column space of A is equal to the row space of A transposed. At the same time, we note that the row space of A transpose is equal to the row space of R. Okay, therefore a basis for the row space of A transpose are taken from the non-zero rows of R. So we have 1, 1, 0, 1. So I make a note here, non-zero rows of matrix R, which is the row echelon form of matrix A transpose. Therefore, this implies that a basis for column space of A, which is equal to the row space of A transpose, is equal to 1, 1, 0, 1. These are essentially the same vectors as these two, except that they are now in column vector form. Now for part B, I shall not elaborate further because the procedure is exactly the same. I will just show you the answer and then you can check against your own answer. You can pause the video at any moment. So this is a basis for the row space of A, and this is a basis for the column space of A. Now finally, let's summarize what we have learned about computing the column and row spaces of a matrix. Suppose A is an n by n matrix that has been reduced to its row echelon form R. We have different methods of computing the column space of A and the row space of A. Method 1, for column space of A, the columns of A corresponding to the pivot columns of R will form a basis for the column space of A. On the other hand, the rows of A corresponding to the non-zero rows of R, taking into account any row swaps, will also form a basis for the row space of A. For method 2, for row space of A, because of the previous theorem that says that the row space of A is equal to the row space of R, therefore, the non-zero rows of R will also form a basis for the row space of A. For method 3, the column space of A is equal to the row space of A transpose. Conversely, the row space of A is equal to the column space of A transpose. Now, the disadvantage of this method is that you need to row reduce A transpose. Of course, the easiest method of computing the column space of A is just method 1, the columns of A corresponding to the pivot columns of R. And for row space of A, the easiest method is method 2, the non-zero rows of R. Now, under what circumstances do we have to use method 1 to compute the row space of A? When the question asks you to compute a basis for the row space of A using only rows from the matrix A, then you will have no choice but to use either method 1 or method 3. So I have come to the end of this lesson. If you have any questions, please leave your comment below the video and I shall respond to you as soon as I have time. Thank you and see you in the next lesson.